How deep can we dive into the depths of matter? What lies hidden in this invisible world where the laws of physics seem to defy our logic? Dear traveler, greetings. Today, we embark on a journey into the infinitely small, a strange universe where particles can be in several places at once, where matter and energy are one, and where the void itself pulses with frenetic activity. A world where atoms, once thought indivisible, reveal a swarm of subatomic particles in a perpetual quantum dance. From quarks to electrons, via the mysterious Higgs boson, join us on a dizzying journey to the heart of matter, where dimensions are measured in billionths of a meter, and each discovery brings us a little closer to the fundamental secrets of our reality. But before setting off on another adventure, remember to like the video and subscribe to the channel so you don't miss anything. Let's begin our journey starting from the human scale, which is about a meter or 39 inches. An average-sized human is 175 centimeters or 69 inches tall. That's 175 times the size of a fly, which measures 1 centimeter or 0.4 inches. Even smaller than a fly, the grain of rice is measured in millimeters. At this scale, the difference between a grain of rice that is 5 millimeter or 0.2 inches and a mite that is 1 millimeter or 0.4 inches is enormous. The grain of rice is 5 times the size of our mite. This is equivalent to the difference between our 1.75 meter or 69 inches tall man and a building 9 meters or 30 feet high. If we continue our journey towards the infinitely small, we must once again change units of measure, using the decimillimeter, then the micrometer. At this scale, we can distinguish the thickness of a hair with a diameter of 50 to 100 micrometers. This is already 35,000 times less than our starting human. In the same order of magnitude, a pollen grain measures 20 to 55 micrometers. Grains of these dimensions can be found by the thousands on the legs of a 15 millimeter or 0.6 inches bee. We've reached the limit of what the human eye is capable of seeing unaided. These dimensions seem tiny, yet we are still far from the infinitely small. A bacterium measures between 1 and 10 micrometers. To a virus, which measures between 10 and 400 nanometers, it seems enormous. The nanometer cannot be distinguished with the naked eye. We have entered the realm of chemistry. The nanometer is used to measure DNA, molecules, and even the atom. A DNA helix has a diameter of 2 nanometers. A water molecule measures less than 1 nanometer. You would need to line up 500,000 to match the thickness of a hair. The atom is even smaller. It measures only 1/10 of a nanometer or 100 picometers. Scientists once thought the atom was the smallest possible scale. The name atom comes from the Greek indivisible. For Greek philosophers, the atom designated the smallest grain of matter, the limit of the infinitely small. But in reality, we are still far from it. The atom is made up of different elements, even smaller. The size difference between the atom and the elements that make it up is equivalent to the difference between a bee and a building. The atomic nucleus is 10,000 times smaller than the atom itself. It measures a few femtometers, with a femtometer representing 1,000th of a picometer. It is made up of neutrons and protons 10 times smaller, themselves made up of quarks of 2 types, up and down, elementary particles whose precise size is unknown. Have we reached the end of our journey? Not yet, and we're far from it. From our 1.75 m or 69 inches man, we have only traveled halfway to the smallest unit of length that exists, Planck length. The Planck length has never been observed or measured. It has only been theorized. It represents the scale of length at which gravity ceases to be valid unless one resorts to quantum mechanics. Other units of measurement have been created to describe the scales of magnitude that separate the atomic nucleus from the Planck length: the atometer, or 410 or 11 inch, the zeptometer, or 410, 12 inch, the yoctometer, or 410/15 the rontometer, or roughly 110/24 and the quectometer, or 110/27. We are in the realm of particle physics, the science of studying elementary particles. The goal of this discipline, to understand the world around us by breaking it down to its most elementary constituents. We long believed that it was the atom, but discoveries over the past 2 centuries have shown us that there is actually a large number of elementary particles, which are even more fundamental constituents of matter. On this journey to the heart of the infinitely small, we will explore these most elementary particles of matter, these particles that make up all the objects around us, from the smallest objects, invisible to the naked eye, to the largest objects, such as planets and galaxies. We will dive into the heart of particle physics, tracing the history of the discovery of the atom and the advances made in recent years. Are you ready for this fabulous journey to the heart of matter? Our journey begins now. To understand how our modern vision of matter was built, we need to go back more than 2,400 years. Anaxagoras is the first Greek philosopher to establish himself in Athens, which will later become a flourishing center of philosophy. He teaches there for about 30 years, counting among his students Pericles, Euripides, and, according to some hypotheses, Socrates. Contrary to the atomist view of Leucippus and Democritus, Anaxagoras does not conceive of matter as composed of indivisible atoms, but rather as an infinity of elementary particles that he calls homoeomeres. According to him, all substances contain a part of all others within themselves. There are therefore no ultimate elements like atoms, but only aggregates of particles containing all possible qualities in varying proportions. As a result, he opposes the idea that matter can be reduced to indivisible and distinct particles, as later posited by Leucippus and Democritus. Indeed, Anaxagoras rejects the notion of an ultimate division of matter and criticizes atomism by comparing it to the crude work of a lumberjack, who would separate matter with an axe. Although he doesn't speak of atoms in the way we understand them today, his conception of matter as composed of infinitesimal and perpetually mixed particles anticipates some modern reflections on the microscopic composition of matter. However, he had no experimental proof to support his theory. Leucippus and Democritus will later develop a different approach. They will claim that all matter is composed of indivisible and unbreakable particles, which they will call atoms. According to them, these particles are separated by void. It is the model of discontinuity. The properties of different substances would, according to him, be explained by the distribution of atoms in matter. For example, lead is heavier than cork because the atoms are more packed there. 100 years later, Aristotle also takes up the ideas of Anaxagoras and Democritus, but he modifies the model of discontinuity. For him, atoms are not separated by void. All space is occupied by matter. It's the model of continuity. Unlike Democritus, who believed that atoms were indivisible, Aristotle thinks matter is infinitely divisible. Each substance around us is made up of 4 elements: earth, fire, air, and water in varying proportions. Today, we know that Democritus's model was closer to reality. However, at the time, people believed more in Aristotle's theory. The theory of the atom would remain unchanged for centuries until the beginning of the 19th century. Between 1803 and 1807, the English chemist and physicist John Dalton proposed his atomic theory. Unlike Democritus and Aristotle, Dalton built his model on scientific bases. He observed that some gases dissolve better in water than others. He then proposed the following hypothesis to explain this phenomenon. If some gases dissolve more than others, it is because the atoms that constitute them have different masses. By studying the works of chemists Joseph Proust and Antoine Laurent de Lavoisier, he observed that each substance always divides into the same products and in the same proportions. Lavoisier notably showed that during a chemical reaction, the mass of the reactants before the experiment is always equal to the mass of the products after the experiment. Hence his well-known phrase, "Nothing is lost, nothing is created, everything is transformed. From these observations, Dalton proposed an atomic theory articulated around 4 points. Matter is composed of small, invisible, and indivisible particles, atoms. Within the same element, the atoms are identical, meaning they have the same properties and the same mass. However, atoms of different elements have different properties and masses. Atoms can combine to form a new substance. The resulting molecule has different properties from the atoms that constitute it. In 1869, the Russian chemist Dmitry Ivanovich Mendeleev classified all the elements into a periodic system according to the increasing order of atomic weights. This is the famous periodic table of elements that appears in all chemistry books today. Of course, the first version of this table wasn't exactly the same as the one studied in chemistry class today. The electron had not yet been discovered. It would take nearly 30 more years. Likewise, the structure of the atom was not yet known. The atomic nucleus would not be discovered until 1911, and it was not until 1912 that the atomic structure of matter would be confirmed by the German physicist Max von Laue. Mendeleev based his periodic table of elements on his intuition and experimental observations. During his research, he noted a periodicity of the chemical properties of elements based on their mass. This periodicity would later be scientifically confirmed. Gradually, Mendeleev's table, which initially counted 63 elements, was completed. It now includes 118 elements. Among these elements, some will eventually disappear from the surface of the Earth, such as uranium, element 92. Others are 100% artificial, like fermium, element 100, which was discovered in 1952 during the American Operation Mike, the explosion of the first H-bomb. In 1897, the British physicist Joseph John Thomson discovered the electron while conducting experiments in a cathode tube. The cathode tube includes a negative electrode, the cathode, and a positive electrode, the anode. By applying an electric current to these electrodes, scientists observed a light beam that seemed to originate from the cathode ray. What is the nature of this ray? Thomson tried to solve this mystery. He then realized that the cathode ray was composed of small particles smaller than an atom and negatively charged. He named these particles electrons. Thomson then supposed that the atom is not indivisible. It is partly made up of electrons. In 1904, he proposed a new atomic model articulated in 3 points. The atom is not indivisible, since it is possible to remove electrons from it. The atom is a ball of positive matter dotted with small negative grains, the electrons. The negative charges of the electrons are balanced by the positive charge of the ball. Result, the atom is neutral. Thomson's atomic model is called the plum pudding model. The positively charged matter ball is comparable to the bread portion, while the negative electrons are the raisins. This model would only be modified a few years later by the New Zealand physicist Ernest Rutherford, a student of Thomson, who discovered the atomic nucleus in 1911. Rutherford was interested in radioactivity. In his time, it was discovered that radioactive elements emit different types of radiation. Among these types of radiation is alpha radiation, which consists of positively charged particles. Based on these observations, Rutherford conducted an experiment that would mark the history of particle physics. He bombarded a thin gold foil with alpha radiation particles, which are positively charged, and noticed that the majority of these particles passed through the foil. However, some deviated from their path, a rather strange observation. Here's what he concluded. The atom is mainly composed of empty space, since most particles pass through the foil. The atom has a small, dense nucleus at its center, upon which particles bounce off or deviate from their trajectory. This small, dense nucleus is made up of positive particles, the protons. An atom is neutral because it contains as many electrons as protons. This model has some limitations. For example, it does not explain why the electrons, which are negatively charged, do not crash into the positively charged nucleus. It is the Danish physicist Niels Bohr, a student of Rutherford, who would fill these gaps. He assumed that electrons move in orbits, called electron shells. Each of these electron shells corresponds to a specific energy level. The further away the electron is from the nucleus, the higher its energy. Electrons can move from one shell to another. If energy is supplied to an electron, it will move to a higher shell, but it won't stay there. It will fall back to its original shell. In doing so, it loses energy and emits light. Each element of the periodic table emits a different light based on its specific light spectrum line. The Rutherford-Bohr model can therefore be summarized as follows. The atom is represented by an almost empty space with, at its center, a dense nucleus containing protons. The electrons, meanwhile, move around the atom's nucleus on the electron shells. There can be more than one electron per electron shell. The atom contains as many electrons as protons. It is therefore neutral. Once again, this model has limitations. It does not explain why the protons, all positively charged, remain bound together in the nucleus instead of repelling each other. In 1932, British physicist James Chadwick would provide an answer to this question with the discovery of the neutron, a new particle located in the atom's nucleus. The neutron, as its name implies, has no electrical charge. In the nucleus, neutrons bind to the protons and keep them from repelling each other. This is what makes the atomic nucleus stable. This model is known as the simplified atomic model. In the years that follow, our understanding of the atomic model will become increasingly complex with the discovery of new particles. As they are discovered, physicists have constructed a precise image of the atom, a particle composed of a nucleus, made up of protons and neutrons at the center and electrons around it, at a distance 10,032,808 times greater. This description of the atom would become more complex later, particularly with the advent of quantum physics. What do we know today about the atom? What are its particularities? To find out, we are going to dive into the heart of matter. At the beginning of the 20th century, Rutherford's experiments caused a surprise. As we have seen, the New Zealand physicist and his team bombarded a gold foil with alpha particles, helium nuclei coming from radioactive elements. The alpha particles have a staggering speed, around 1/10 the speed of light, or about 18,740 miles per second. They therefore expect the same result as if cannonballs were fired at a sheet of paper. However, against all expectations, some particles bounce back. It was discovered then that the nucleus of the atom is extremely dense. This experiment paved the way for numerous studies and research on the atomic nucleus. Gradually, physicists discovered that some atomic nuclei are radioactive, which means they can change in nature. This change can occur spontaneously or in the laboratory as a result of nuclear reactions. Physicists then isolated the protons and neutrons in the atomic nucleus to better understand the different types of radioactivity. They realized that only 5% of known nuclei are stable. The unstable nuclei, those that decay, therefore represent the majority of atomic nuclei. Today, the atomic nucleus is described based on its number of protons and its number of neutrons. Let's return to Mendeleev's periodic table of the elements. At the top left, you can read the atomic number of each element, which is the number of protons contained in an atom of that element. When we move our cursor in this table from top to bottom and from left to right, the atomic number increases, as does the atomic mass. Which makes sense. The mass of the atom is the sum of the masses of the protons and neutrons it contains. Thus, the lightest elements, like helium, are generally at the top of the table, while the heavier elements, like uranium, are at the bottom. Isotopes are atoms that have the same number of electrons, and therefore protons. Indeed, in an electrically neutral atom, there are as many negatively charged electrons as positively charged protons because the neutrons are neutral. There are about 325 known natural isotopes and 1,200 created artificially. The isotopes of the same element have identical chemical properties, but different physical properties. An element can be stable, and its isotope radioactive. Let's take some examples. Hydrogen has 3 isotopes. Classical hydrogen, symbol H, which has 1 proton and 0 neutrons. Deuterium, symbol 2H, which has 1 proton and 1 neutron. And finally, tritium, symbol 3H, which has 1 proton and 2 neutrons. Hydrogen and deuterium are stable, but tritium is radioactive. Another example, uranium has 17 isotopes, all of which are radioactive. They all have 92 protons, but have between 125 and 150 neutrons. Uranium-238 is naturally present on Earth, as are uranium-234 and uranium-235. The other isotopes have been created artificially. Among the unstable nuclei, some decay very quickly, while others decay extremely slowly. The average decay time is called the lifespan. The lifespans of radioactive nuclei can range from a nanosecond to a time longer than the age of the universe. For example, carbon-14 has a lifespan of about 50,000 years, making it useful for determining the age of organic remains. Carbon-14 is constantly produced by nuclear reactions around us when particles from space collide with the nitrogen in our atmosphere. Living beings continually regenerate carbon-14 in their bodies when they consume food. But when they die, carbon-14 is no longer renewed. It decays gradually. This means that the rarer the carbon-14, the longer ago the organism died. When a nucleus is unstable, it will decay through a nuclear transformation to stabilize. This stabilization is accompanied by one or more types of radiation: alpha radiation, beta radiation, and gamma radiation. Thus, we distinguish several types of radioactivity. The first two, alpha and beta, are particles, while the third, gamma, is electromagnetic in nature. Today, radioactivity is classified according to the force responsible for their decay, rather than the emitted radiation. A nucleus can decay through one of 3 interactions: electromagnetic interaction, strong interaction, or weak interaction. Each of these major classes can be further divided into several types of radioactivity, depending on the emitted particles: double beta or double gamma radioactivity, double or triple proton radioactivity, cluster radioactivity. Some types of radioactivities have been predicted by theory, but have not yet been observed in physicists' experiments. There could be about 7,000 atomic nuclei. Today, over 1/500 are cataloged, of which 325 are natural. The atomic nucleus is just one of the many components that make up the atom. After the discovery of the electron in 1897 by Thomson and the discovery of the atomic nucleus in 1911, new particles would be discovered. In 1915, the German physicist Albert Einstein proposed a revolutionary theory, the theory of general relativity. This theory complements the theory of special relativity, which he published in 1905. To understand this theory, let's go back a bit further in time. In the 1880s, American physicists Albert Abraham Michelson and Edward Morley conducted measurements of the speed of light and were surprised to find that it remained constant regardless of the direction in which it was observed. Yet, it should have been different depending on the angle of measurement. The speed of light should be greater when measured parallel to the Earth's motion, rather than perpendicularly. This puzzle intrigued Einstein. The scientist delved into the matter. As a result of his research, he reached a radical conclusion. He challenged the absolute nature of space and time. This is special relativity. This theory revolutionizes our view of the world by considering that a second does not always last a second, and a meter does not always measure a meter. The speed of light then becomes a fundamental constant whose value never changes. Wherever the observer is located, it will always be 299,792 kilometers, or 186,282 miles per second. Consequently, if the distance of light does not vary, it means that distances must contract and time must dilate for the moving Earth-based observer. Time slows down for objects in motion, a revolutionary theory that would indeed be experimentally verified later. An atomic clock is taken aboard an airplane for several hours, while a second clock remains on Earth, stationary. Upon its return to Earth, a tiny difference is found compared to the clock left behind. Like any theory, the theory of special relativity has its limits. It does not incorporate Newton's law of gravity, which is essential to our understanding of the world. In 1915, Einstein proposed the more complete theory of general relativity. He then postulated that gravitation is no longer a force exerted by one object on another, but a deformation of the structure of space-time. While Newton thought that it was the Earth creating a force around it, endured by the Moon, Einstein postulated that the Earth creates a deformation in space-time, and that the Moon, which experiences no force, moves in a straight line, a trajectory that becomes curved, with the deformation of the universe. The theory of general relativity thus explains that the gravitational attraction between masses is caused by the deformation of space and time by these masses. It also explains that space-time curves the more massive the nearby mass is. Shortly after Einstein's theories were published, quantum mechanics was discovered. Physicists sought to integrate the principles of general relativity with those of quantum mechanics. At the beginning of the 20th century, relativity and quantum mechanics were the pillars of particle physics. But the link between the two remained uncertain. These theories primarily allowed for a better understanding of the world we live in, which led to the discovery of new particles. In 1928, the British physicist Paul Dirac attempted to combine relativity and quantum mechanics to better describe the electron. During his work, he postulated the existence of the positron, a particle associated with the electron of the same mass, but with opposite charge. The existence of positrons was confirmed in 1932 by the American physicist Carl David Anderson while studying cosmic rays by taking snapshots of high-energy particles coming from space. It would take another 20 years to describe the electromagnetic interaction between charged particles like the electron and the positron. At the same time, James Chadwick discovered the neutron, a neutral particle located in the nucleus of the atom. A few years later, in 1936, Anderson made another discovery in cosmic rays, a particle about 200 times more massive than the electron, with the same electrical charge. It's the muon. This particle behaves like a very massive version of the electron. It is unstable and would decay very quickly into an electron. This discovery then left many physicists puzzled. What could be the purpose of the muon? How can it be integrated into our theoretical models? This is just the beginning of a constant questioning of our knowledge. In the 1950s, physicists used particle accelerators to create collisions between particles. They conducted increasingly energetic collisions to better understand matter. To their surprise, they discovered a wide variety of new particles, Hyperion, Omega, Cassini. These particles are sensitive to the strong interaction, the same force that holds protons and neutrons together in atomic nuclei. But what surprises physicists is their number. While they were looking for a limited number of elementary particles, they found themselves with a multitude of particles whose roles they did not yet precisely understand. It was then, in 1964, that quarks were discovered. This discovery would change everything. The group formed by protons and neutrons, bound together by the strong interaction, is named nucleon. In the mid-20th century, it was believed that nucleons were the elementary building blocks of matter. But in 1968, experiments conducted at the Stanford Linear Accelerator Center in the United States revealed the existence of an internal structure within nucleons. These experiments were supplemented by others, which confirmed the presence in protons of new particles, which would be called quarks. By the late 60s, 3 quarks were known: U, D, and S. In 1974, the C quarks were discovered. In 1977, the B quarks. Then, in 1995, the T quarks. There are now 6 types of quarks: the quark up, or U, the quark down, or D, the quark strange, or S, the quark charm, or C, the quark bottom, or B, and the quark top, or T. As a side note, their name comes from James Joyce's novel, Finnegan's Wake. New particles that belong to the lepton family, like the electron and the muon discovered by Anderson, are also gradually discovered. Like quarks, there are 6 charged leptons: the electron, the muon, and the tau on one hand, and on the other hand, the low-mass neutral leptons, the electronic neutrinos, the muonic, and the tauic. The first 3 carry a charge of E, and the last 3 are without charge. Unlike quarks, leptons are insensitive to the strong interaction. By the end of the 20th century, we finally found all the elementary particles that make up matter, the 6 quarks and the 6 leptons. To this list, we must add antiparticles. We have already mentioned the positron, the antiparticle of the electron. Its characteristics are identical to those of the electron, but its charge is plus E. Each elementary constituent has its antiparticle. Neutrons and protons are therefore not the elementary constituents of matter. They are made up of trios of quarks. A proton is composed of 2 up-type quarks and 1 down-type quark. A neutron is composed of 2 down-type quarks and 1 up-type quark. These quark triplets allow for multiple combinations, hence the wide variety of particles observed in particle physics experiments. We do not know if there is anything inside quarks, but what we do know is that quarks are smaller than 1/billionth of a meter, or approximately 0 inches, non-measurable, and that they seem elementary. At the end of the 20th century, there was a better understanding of the nature of the strong interaction, which holds quarks together, as well as protons and neutrons. A better understanding of the weak interaction, responsible for certain types of radioactivity, was also beginning to emerge. This was partly due to the discovery of new particles, the W and Z bosons, which are themselves elementary particles. The W and Z bosons were discovered in 1983 by CERN. The Z boson is neutral. The W boson, however, is a charged particle existing in 2 forms, W plus and Wi. These 3 bosons, Z, W plus, and W, are what are called gauge bosons. They act as carriers of an interaction, the weak interaction. They are, in a sense, mediating particles. These particles have a very heavy mass, which at the time remained unexplained. While the photon has no mass, the bosons have a mass nearly 100 times that of a proton, or 220 pounds. There was no understanding as to why some particles have mass and others do not. In the 1970s, physicists Robert Brout, François Englert, and Peter Higgs hypothesized that particles acquire mass by interacting with an invisible but omnipresent field in the universe, named the Higgs field. Here is their theory. Immediately after the Big Bang, the Higgs field had a value of 0. Then, as the universe began to cool, the Higgs field increased and imparted mass to all particles interacting with it. The more a particle interacts with the Higgs field, the more massive it becomes. Particles that do not interact with the Higgs field, like photons, are massless. This phenomenon by which particles acquire mass is called the Brout-Englert-Higgs mechanism, named after the theorists of the Higgs field. The Higgs field is associated with the Higgs boson, which is, in a sense, the visible manifestation of this field, a bit like a wave on the surface of the sea. Indeed, in the current description of nature, each particle is a wave in a field. For example, light is both a wave in the electromagnetic field and a stream of particles, the photons. In the case of the Higgs boson, the field appeared first. The Higgs boson is a wave inside this field present ever since the Big Bang. While in the 1970s, all the foundations of particle physics were laid, the Higgs boson still needed to be discovered experimentally. The problem is that the Higgs boson cannot simply be found in nature. It must be produced during a particle collision and then decay into other particles, which can then be identified by a particle detector. This is a real challenge for physicists because the Higgs boson only appears in 1 in a billion collisions. Therefore, it is necessary to meticulously analyze enormous amounts of data to hope to detect this mysterious boson. In 2012, the Higgs boson was finally discovered at CERN. More precisely, a type of Higgs boson was discovered. It would naturally be called the H boson. The H boson is a particle without electric charge with a short lifespan. As predicted by the theory, it decays rapidly. How did they know that the particle discovered at CERN in 2012 was the Higgs boson? In quantum physics, particles have several peculiarities: electric charge, mass, and also spin. Spin is a quantum characteristic of particles related to their rotation properties. The theory predicted that the Higgs boson had 0 spin. This is indeed the case with the particle discovered in 2012. The data, of course, are examined multiple times to confirm the observations. It was only in March 2013 that the discovery of the Higgs boson was officially announced, the beginning of a new chapter. Over the next 10 years, scientists will study the interactions between the Higgs boson and other particles. In 2016, the interaction of the Higgs boson with the tau lepton was discovered, and then in 2018 with the top and bottom quarks. All these discoveries were made possible by ultramodern technologies. The discovery of the Higgs boson in 2012 was made possible by the Large Hadron Collider, or LHC. The LHC is a ring-shaped collider that accelerates billions of protons or atomic nuclei to discover new phenomena and thus new particles. It is the world's largest and most powerful particle accelerator. Its circumference reaches nearly 27 kilometers or 17 miles. Managed by CERN, it is buried 100 meters or 328 feet underground at the French-Swiss border. The first collisions within the LHC took place on March 30th, 2010. The objective, which has since been achieved, was to discover the Higgs boson. This particle accelerator has another mission: to study the quagma, the plasma of quarks and gluons produced by heavy ion collisions. This state of matter may be found in some neutron stars. It is also believed to have existed in the very early moments of the universe. Within this accelerator, the protons travel around the circular ring at a dizzying speed, extremely close to the speed of light. They circle the ring almost 11,050 times every single second. The protons travel in a vacuum tube, allowing them to encounter no obstacles on their path. The LHC has 4 collision points where particle beams collide nearly 40 million times per second: Atlas, CMS, LHCb, and ALICE. Around these 4 collision points, 4 large particle detectors are installed. While the operation of this particle accelerator may seem relatively simple, the technology required to develop it is extremely innovative. Nearly 10,000 superconducting magnets are used to maintain an extreme magnetic field. These magnets must be cooled with superfluid helium to a temperature of 270 degrees or 456 degrees, a temperature colder than outer space. Each particle beam consists of several thousand proton bunches separated by a few meters distance. Each bunch is composed of over 100 billion protons. The energy of all these protons combined is phenomenal, 360 megajoules, equivalent to the energy of a high-speed train traveling at full speed. The collisions between particles require extreme precision. Once a collision has occurred, a multitude of particles is released. They must then be analyzed using particle detectors. For this, physicists investigate what happened during the collision. What particles are present? What are their trajectories? What are their characteristics? That is, their energy, mass, charge. And that's not all. To perform this meticulous work, it is necessary to stack several layers of detectors. Each layer identifies a specific type of particle. Preparing this technological gem took 2 decades. The entire world participated in the development of the LHC, which was finally assembled at CERN. Following its first collisions in 2010, the LHC gradually improved its performance. In 2012, it completed a first phase of data collection, the Run 1. Run 1 primarily facilitated the discovery of the Higgs boson and the measurement of some of its characteristics, such as its mass. It also enabled ultra-precise measurements to test the standard model on which particle physics is currently based. The LHC helped to better understand the strong interaction and the weak interaction. In 2013, some elements of the LHC were repaired or replaced to make performance even more precise. In 2016, the second data collection phase, Run 2, was launched. Run 2 confirmed the characteristics of the Higgs boson and continued to precisely measure the processes of the standard model. A new phase is being prepared. It is scheduled for 2025. The objective, to increase the number of collisions by a factor of 100 compared to Run 1. Because the more collisions that are made, the more likely we are to access rare phenomena, detect new particles, and push the boundaries of our knowledge. We have finished our journey to the heart of matter. Isn't it strange to think that the world around us, as complex as it is, can be reduced to a small number of elementary bricks? At the beginning of the 20th century, we thought these elementary bricks were atoms. Gradually, during the 20th century, and then at the turn of the 21st century, we realized that atoms themselves are made up of even more fundamental elements, quarks, leptons, and bosons. To make all these discoveries, we had to probe ever smaller distances with increasingly energetic particle collisions. We also discovered during the 20th century that alongside elementary particles, there are unexpected, heavier particles. These particles are unstable. They disintegrate very quickly. We began to describe the interactions that affect them. In 2012, the discovery of the Higgs boson added the last piece to the puzzle, completing and confirming the standard model. Today, physicists seek to test this standard model, but also to discover new particles and new interactions to push the limits of our knowledge of the world. Exploring the infinitely small is a real challenge for physicists who have had to build ever more sophisticated instruments to probe matter. There is no microscope powerful enough to probe matter at distances of a millionth of a billionth of a meter, about a quadrillionth of an inch. As a result, high-tech, ultra-precise devices had to be developed. Scientists use colliders or particle accelerators like the LHC, which are essential for their research in particle physics. These ultra-powerful instruments make it possible to guide particles to a precise destination, usually a particle detector. In this context, to accelerate does not mean to increase the speed of particles. Since Einstein's theory of relativity, we know that the speed of light is the limit. nothing goes faster than light. When particles are launched at an extreme speed, close to that of light, their speed cannot be increased. In particle physics, to accelerate means to increase the energy of the particles. The particle accelerator will provide the particles with a certain amount of energy rather than increasing their speed. A particle accelerator can accelerate various types of particles: electrons, protons, ions. Particles that differ in size and mass but have something in common. They are charged particles. An accelerator will not be able to accelerate neutrons, for example. The collider uses an electric field to create a force on a charged particle, the Lorentz force. To express the energy of a particle, we will not use the joule but another unit of measurement called electron volt, abbreviated as EV. 1 EV corresponds to the energy gained by an electron subjected to a voltage of 1 volt. We generally talk more about millions of electron volts, or MeV. Depending on the accelerator used, the final energy of the particle will be from a few thousand electron volts to TeV, a tera electron volt. 1 TeV is a million times higher than 1 MeV. Particle accelerators can vary greatly in size, from a few dozen centimeters or inches to tens of kilometers or miles. Logically, the larger the accelerator, the higher the energy it can achieve. There are two main categories of accelerators: circular accelerators like the LHC, and linear accelerators. In circular accelerators, the particles move in circles and pass several times through the acceleration systems, gaining energy with each lap. These accelerators are very efficient, but the beam guidance can be more complex. The particles must be deflected to follow a curved trajectory. In doing so, they emit light called synchrotron radiation, which causes the beam to lose energy. The second main category of accelerators is the linear accelerator. In this type of accelerator, the particles pass only once through each structure that makes up the accelerator. This technology is less efficient, but has the advantage of facilitating the guidance and control of the particle beam. Particle accelerators have many applications beyond research in particle physics: nuclear physics, metallurgy, sterilization, health, cancer treatment. Today, the most powerful particle accelerator gives protons energies 10 million times higher than the probe used by Rutherford in 1911. In particle physics, physicists strive to identify the present particles to better understand the physical processes at play. However, particles cannot be seen directly. Just like an animal leaving tracks in the sand, particles leave traces of their presence, which are collected and analyzed using particle detectors. Thus, particle detectors help us establish the identity card of particles: speed, mass, electric charge. Particles are all different. Some particles are heavy, others light. Some live very long, while others disintegrate very quickly. That's why particle detectors are designed with a layered structure, a bit like Russian nesting dolls. Each layer contains an apparatus playing a very precise role in detecting particles. To see the infinitesimally small, we need enormous detectors, which are the height of buildings of 4 to 8 stories, or 40 to 80 feet, and weigh as much as several thousand elephants. Why do detectors need to be so large? Because particles travel at such speed, under the effect of such colossal energy, that significant thickness is required to stop them. The higher the energy of the particles, the denser and thicker the material needed to stop them. Particle detectors analyze how particles lose energy. The lost energy is converted into electrical signals, and these electrical signals are processed to identify the particles. The particle detector comprises several elements. First, there is the tracking detector, which identifies the trajectory of the particles. The magnetic field curves the trajectory of electrically charged particles. The curvature of the particle's trajectory allows us to deduce their momentum. Highly energetic particles will have an almost straight trajectory, while low-energy particles will have a spiral trajectory. Then there is the calorimeter, which stops, absorbs, and measures the energy of particles partially or totally lost when they pass through a material. The calorimeter consists of several layers of absorbing materials, like lead, followed by layers of detecting materials, like liquid argon. Electromagnetic calorimeters measure the energy of photons and electrons, and hadronic calorimeters measure the energy of hadrons, which are particles composed of quarks when they interact with atomic nuclei. Examples of these are protons and neutrons. Calorimeters stop most particles, except muons and neutrinos. The particle detector contains additional layers after the calorimeter. The first is a detector specially designed to detect muons. The second is a neutrino detector. These detectors generate electrical signals which are digitized and analyzed. Not all these signals can be recorded. They must be sorted quickly to keep only one event in 400,000. A difficult choice. Sorting these signals is accomplished by several thousand PCs working simultaneously. After signal recording, a massive task of selecting interesting events must be undertaken before performing measurements. The analysis of collected data is truly a titan's task. Thousands of researchers, engineers, and technicians work together, and each published result is the fruit of the collaboration of several researchers. All these advanced instruments have allowed us to establish what is known today as the Standard Model. The role of the Standard Model is to describe the elementary particles and how they interact with each other. It was constructed between the second half of the 20th century and today. It is capable of understanding and predicting a wide variety of phenomena, except gravitation. Like the periodic table of elements, the Standard Model identifies and categorizes the elementary particles based on their characteristics. We distinguish matter particles, the fermions, from interaction particles, the bosons. There are 12 fermions, divided into two categories, the 6 quarks and the 6 leptons. The 6 quarks are the up, down, strange, charm, top, and bottom quarks. The 6 leptons are the electron, muon, tau, and their associated neutrinos. Each category is organized into 3 families, or 3 generations. A generation contains a pair of quarks and a pair of leptons. The first generation contains the lightest and most stable particles. These particles make up the ordinary matter around us. The third generation contains the heaviest and most unstable particles. The bosons are the messengers of the fundamental interactions. There are 12 of them, like the fermions. The photon, which carries the electromagnetic interaction, the W plus W, and Z bosons, which carry the weak interaction, and the 8 gluons, which carry the strong interaction. For each of these particles, there exists an antiparticle, which has very similar properties. For example, the positron is the antiparticle of the electron. Its characteristics are the same, but its charge is positive. The W plus boson is the antiparticle of the W boson. What about neutral bosons? That is, the photon, the Z boson, and the gluons. Each neutral boson is its own antiparticle. One must know that a particle cannot coexist with its antiparticle. In each other's presence, the 2 particles will annihilate and create new particles. 2 photons annihilate, just as an electron and a positron. Theoretically, at the birth of the universe, there were as many particles as there were antiparticles. So, how is it that we live in a world of matter? This is one of the great mysteries of particle physics that the Standard Model has yet to explain. To this list of elementary particles, we must not forget to add the Higgs boson, which explains why the Z, W+, and W bosons are massive, while their mass should be 0. The Standard Model of particle physics explains most physical, chemical, and biological phenomena by describing 3 of the 4 fundamental interactions. the electromagnetic interaction, responsible for electricity, magnetism, and chemical bonds. The weak interaction, involved in radioactive decay and certain nuclear reactions. The strong interaction, which ensures the cohesion of protons and neutrons within atomic nuclei. However, the Standard Model does not include the gravitational interaction, which is separately described by Einstein's general relativity. Gravity remains poorly understood at the quantum scale, and unifying the Standard Model with gravity into a quantum theory of gravity is one of modern physics' greatest challenges. A fundamental interaction is a reciprocal action between elementary constituents. Each interaction is mediated by a boson. The electromagnetic interaction is the most well-known fundamental interaction. It concerns all charged particles, and its mediator is the photon. Its range is infinite. It can be repulsive between two particles of the same charge, or attractive between particles of opposite charges. This interaction is responsible for all electrical, light, and magnetic phenomena. It holds atoms together. The strong interaction is the most intense interaction. It is 100 times stronger than the electromagnetic interaction. It concerns quarks and ensures the cohesion and stability of atomic nuclei. It is mediated by gluons. Unlike the electromagnetic interaction, its range is not infinite. It is limited to 1 femtometer or 3.3 femtoinches, 10 to the power of negative 15 meters, or 10 to the power of negative 13 inches, which corresponds to the size of nuclei. The weak interaction has a very low intensity, 100,000 times weaker than the strong interaction. It concerns all matter particles. It is mediated by W and Z bosons. Its range is limited to 1 attometer or 3.9 ATU inches, 10 to the power of negative 18 meters, or 10 to the power of negative 16 inches, a smaller distance than the size of an atomic nucleus. This fundamental interaction is weak, but it is nevertheless the origin of nuclear fusion in stars like the Sun. It is also responsible for beta radioactivity. Finally, the last fundamental interaction is the only one not explained by the Standard Model. It is the gravitational interaction. It is dominant at the scale of the universe, and its range is infinite. Paradoxically, it is the weakest interaction at the particle scale. It is about 10 to the power of 38 times weaker than the strong interaction. The gravitational interaction concerns all particles. It is responsible for gravity, tides, and astronomical phenomena. Its mediator has not yet been discovered, but it has been theorized as the graviton. It is difficult to describe this paradoxical interaction in the realm of the infinitely small. However, it is described by the theory of general relativity. Special relativity has contributed significantly to the study of the infinitely small. One of the most important contributions is Einstein's famous equation, E = mc2. What does this seemingly simple equation mean? E represents the intrinsic energy of a particle at rest with mass m, or mass energy. C represents the speed of light. This equation means that a particle at rest has energy equal to its mass, multiplied by the square of the speed of light. This equation for the first time establishes the link between energy and matter. It would therefore be possible to transform one into the other, to convert matter into energy and energy into matter. Throughout the 20th century, physicists explored this equivalence between energy and matter and discovered processes that allow the transformation of mass into energy, the fission and fusion of atomic nuclei. What is fission? Some heavy atomic nuclei, such as uranium-235, are said to be fissile, meaning they are susceptible to fission. These nuclei are made up of a large number of nucleons, that is, protons and neutrons. When a fissile nucleus is struck by a neutron, it breaks into two lighter nuclei, the nuclides. The sum of the masses of these nuclides is less than the mass of the initial nucleus. This difference in mass is converted into energy. The fission products are ejected at very high speeds and will heat the surrounding matter by colliding with other atoms. Current nuclear power plants operate on the principle of fission. The heat produced by the process is captured to be transformed into electricity. Fusion represents the reverse mechanism. In some cases, two light atomic nuclei can fuse to form a heavier nucleus. This nuclear reaction occurs naturally in the universe. It is what makes stars shine and allows the sun to transform about 620 million metric tons or 683 million tons of hydrogen into 615 million metric tons or 678 million tons of helium. The difference is then converted into energy, radiated by the sun. This energy allows life on Earth. The theory of relativity is indispensable to particle physics. It is on this equation, E just under mc2, that the principle of the particle accelerator is based. In particle physics, the energy required to study a phenomenon is higher when studying shorter distances because smaller wavelengths are needed. That is why particle accelerators capable of causing very violent particle collisions are used. These collisions create new particles whose mass comes from the energy of the collision. We do not only break existing matter, we also create new matter. The higher the available energy, the more new high-mass particles can be created. Generally, these heavy particles appear only briefly, as they will then decay into lighter particles. But with each decay of a heavy particle into lighter ones, the mass difference is converted into energy. Thanks to the equation E just mc2, we know that matter can be created from energy. This creation of matter, theoretically, goes hand in hand with the creation of antimatter. Antimatter is a form of matter different from the matter around us, called ordinary matter. It is composed of antiparticles, whose properties are very similar to those of the particles that make up ordinary matter. We have seen that for every particle of matter, there is an antimatter particle, or antiparticle, with opposite electric charge, but the same mass and lifespan. We have also seen that a particle and its antiparticle cannot coexist, and they annihilate each other. To study antiparticles, one must act quickly, because they quickly meet ambient matter and annihilate. Although we know how to create antimatter at the same time as ordinary matter in colliders, it still seems strangely absent from our world. A puzzle for particle physics. Why is antimatter so rare? Why do we live in a world of matter and not antimatter? We are reaching the limits of the standard model. As complete as this model is, many questions remain unexplained by the theory. Is there something at even smaller distances? Are there even heavier particles, or new fundamental interactions of very short range? Why are the three families of matter particles identical, but with such different masses? Why are the three fundamental interactions of the standard model so different? Why do they act on certain particles and not on others? How can we account for gravitation, the only interaction not explained by the standard model? How can we link the infinitely small and the infinitely large? What is the nature of dark energy and dark matter, which theoretically should constitute the majority of the universe's energy content? To answer all these questions, physicists use both the knowledge of relativity and quantum mechanics. Using quantum mechanics is necessary, but it complicates matters. For example, if we consider the decay of a heavy particle into several lighter particles, we can consider that one moves from a state A to a state Z through several intermediate states, B, C, D, etc. In any case, that's how classical physics sees things. Because in quantum physics, nothing can be predicted. We must reason in terms of probabilities. All intermediate states are more or less probable. All must be considered, even those that seem much less likely, as they correspond to particles more massive or more energetic than the initial or final state. Let's take an example. It is possible, in quantum physics, to study the decay of a bottom quark into a strange quark and a muon-antimuon pair. In classical physics, such a decay is impossible. This decay requires going through a complicated intermediate state. Here, it's the weak interaction that comes into play. But in quantum physics, it's possible because it's probable. The bottom quark decays into a top quark and a W boson. One of the two will emit a photon, which converts into a muon-antimuon pair. Then the W boson and the top quark recombine to create a strange quark. In the intermediate state, the W boson and the top quark are much heavier than the initial state, bottom quark. To better understand the mechanisms at work in particle physics, it is thus essential to rely on general relativity, producing increasingly violent particle collisions, but also on quantum physics, exploring extremely rare phenomena. The two are complementary. We have reached the end of our journey into the heart of the infinitely small. Over the decades, physicists have managed to build a coherent vision of matter, the Standard Model. But this model has its limitations. Many questions remain unanswered. So, what are the plans for the future? If there are new particles of matter, new interactions, or constituents of matter even more fundamental than the particles we believe to be elementary, we must find them by continuing to probe matter at ever smaller energy and distance scales. In 2025, a new instrument is expected to come into being, the High Luminosity LHC, or HL-LHC. Its goal, to record an amount of data 10 times greater than anything the LHC has previously recorded. This would allow us to measure the properties of the H boson even more precisely, but also to explore very rare decays, like the decay of the H boson into two muons. The HL-LHC will be able to produce even more energetic collisions to produce even more massive particles and in greater numbers. To succeed the LHC, a new circular collider is under study, the FCC. This particle accelerator could be built in China, in a tunnel 80 to 100 kilometers, 50 to 62 miles long. For comparison, let us recall that the LHC is currently in a tunnel of only 27 kilometers, 17 miles. The FCC could then produce proton collisions with unprecedented energy, up to 100 TeV, which corresponds to 8 times the energy of the LHC. This would allow us to produce extremely massive particles. The FCC could also enable us to move from proton-proton collisions to electron-anti-electron collisions, an ambitious project that will require years of preparation, just as the LHC took years to develop. But in the same way that the LHC led to a major discovery, that of the H boson, physicists are confident the FCC could revolutionize the Standard Model and perhaps, once and for all, answer the questions that remain unanswered today.
Thought the atom was the smallest element in the universe, think again. Thanks to extensive research, notably at CERN's particle collider, we now know that every atom is made up of a nucleus and one or more electrons. Most atomic nuclei are made up of neutrons and protons, known as nucleons. Because of the negative electric charge of electrons and the positive electric charge of protons, these two elements are held together by the action of the electromagnetic force. This is one of the 4 great forces that govern the laws of physics as we know it. At the atomic scale, The most important forces are the electromagnetic force, the strong interaction that holds atomic nuclei together, and the weak interaction. The role of the latter is rather difficult to describe, yet still understandable to most people. But it is just as responsible for the radioactive decay of subatomic particles as it is for nuclear fusion at the heart of stars. The final fundamental interaction, and probably the best known of all, is the gravitational force. In other words, gravity. Its intensity depends, above all, on the mass of the objects in question. It is therefore very present on a cosmic scale, whereas its role at atomic levels is negligible. The atom is made up of neutrons, protons, and electrons. But is it possible to go even further? Not surprisingly, the answer is yes. At the heart of nucleons are other elementary building blocks of matter. These are the quarks. And when it comes to their size, things get even more complicated. But to understand better, we need to go back to the structure of the atom. The size of atoms varies according to the element considered, but the order of magnitude remains more or less the same, 10 to the minus 10 degree meters, or 0.1 nanometers. The atomic scale is therefore ridiculously small. An atom is not a ball of matter, contrary to what some simplified representations tell us. In fact, it's more like a ball of vacuum. After all, while the size of an atom is of the order of 10 to the minus 10th power meters, the size of its nucleus is 10 to the minus 15 power meters. The nucleus is therefore 100,000 times smaller than the atom itself. To help you visualize this difference, let's imagine that an atom is the size of a soccer field. How big do you think the nucleus would be in this representation? That of a player? A football? A red card? Well, no. The size of the core would be that of a marble placed in the center of the field. But then, if the nucleus is so small, why give atoms such dimensions? The reason is simple. Electrons must also be taken into account. In theory, electrons are elementary point particles. They have no size or dimensions. Almost all the mass of an atom is therefore concentrated in its nucleus. This is why we say that matter is essentially made up of vacuum. Of course, this is not visible on our scale. It's the forces acting between particles that give us the illusion that everything around us is full. So forget the idea of being able to pass through walls. We also know that electrons move in quantized orbits around the nucleus. Their probability of presence varies from place to place. So without experimental measurements, it's impossible to know the exact position of electrons around a given atomic nucleus using theoretical calculations. They are probabilistic particles subject to the mysterious laws of quantum mechanics. Nevertheless, for each atom, we know the maximum distance of the electrons from the nucleus. And it's this maximum distance that sets the size of atoms at around 10 to the minus 10 power meters. Now back to the size of quarks. Just as electrons give atoms a certain diameter, quarks give protons and neutrons a diameter. And just like atoms, quarks are considered to be point-like particles. In this sense, quarks cannot have a size. However, if they were to have one, it would probably be less than 10 to the minus 18 power meters. That's 1,000 times smaller than a nucleon, itself 100,000 times smaller than an atom. Again, this order of magnitude is so minute that it's impossible for us to conceptualize. But if we make a comparison on our own scale, things become much more meaningful. So let's start by finding a substitute for our quark. To simplify things, let's take a 1-meter object. How about a baguette? Now we need to find something 1,000 times bigger to represent our nucleon. In other words, something a kilometer long. The Burj Khalifa, i.e. the world's tallest skyscraper, at some 828 meters high, would fit the bill perfectly. Well, we've got our quark, we've got our nucleon, now we need our atom. For that, we need something 100,000 kilometers long. Knowing that the Earth is about 12,700 kilometers, or 7,900 miles in diameter, we'll have to look further out, into the cosmos. Saturn, with a diameter of around 116,000 kilometers, or 72,000 miles, is the ideal candidate. So while the atom may seem infinitesimally small to us, it's actually a giant compared to the other components of matter. Just think, next to the atom, elementary particles such as quarks and electrons, if they had any size at all, would be no bigger than a baguette in front of Saturn. That's a bit of an oversimplification, but it does reflect the relative immensity of the world around us. Who knows? Perhaps our universe itself is just a drop of water in something much larger. Once this question has been posed, the answers are limited only by our imagination. Some may think of the multiverse, and others, the disturbing immensity of infinity. In the light of our current knowledge, there's nothing to suggest one hypothesis over another. While studies are underway to determine the nature of the observable universe, what lies beyond it remains a profound mystery. If indeed there is a beyond. We've seen the atom and its components. Let's consider this as a starting point for our fantastic epic journey towards the infinitely large. It's going to be a long road, so it's best to take it one step at a time. The question is, what comes after the atom? And the most logical answer would be molecules. Indeed, a molecule is a structure, sometimes very simple, sometimes very complex, resulting from the bonding of several atoms. To avoid complicating things too much, we're interested in the water molecule. This is made up of 2 hydrogen atoms for 1 oxygen atom. Hence its name, H2O. Its size is in the nanometer range, or 10 to the minus 9 power meters. Again, it's tiny. In fact, it's estimated that a single drop of water is made up of around 3 times 10 to the 20th power water molecules. This quantity is simply mind-boggling. That's 300,000 million billion molecules. That's 300 billion times more than the number of stars in our galaxy. All in a droplet just a few millimeters in size. We can also assume that this drop of water must harbor some form of life. Single-celled organisms capable of growth and reproduction. The smallest of them measure just a few hundred nanometers. This is the bare minimum required to provide the genetic material necessary for the survival of these organisms. Human cells, on the other hand, are in the micrometer range. This means they are 1,000 times smaller than a millimeter, so you need an optical microscope to see them. This is also the norm for most bacteria, which are on average 2 micrometers long. In 2022, researchers at the University of the West Indies published their discovery of a giant bacterium in a mangrove sample. Called Thiomargarita magnifica, the individual cells of this titanic filament-shaped bacterium stretch up to 2 centimeters long. This has never been seen before, pushing back the limits of size among microorganisms. In fact, this bacterium would be visible to the naked eye, provided you pay close enough attention. For Olivier Gros, one of the researchers behind this discovery, it's a bit like observing a primate, the size of Mount Everest. So even on the scale of a single drop of water, the world is much larger than we can imagine. But our journey is far from over, and it's time for us to continue our ascent towards cosmic scales. Still taking a drop of water as our reference, we now need to move on to the size scales of our everyday lives. And what better way to do this than by the liter? To reach this quantity, we need no less than 20,000 droplets. But we can go even further by asking how many drops of water there are in all the oceans that cover the Earth. Several people have had fun doing the math, and the result they come up with is just incredible. Between 2 and 4 times 10 to the 25th power drops of water. That's around 100,000 times more than the number of water molecules in a drop. This puts things into perspective, doesn't it? We can do the same thought exercise, but this time comparing our own scale to that of our beautiful blue planet. To do this, we'll estimate that the average human height is 1.70 meters or 5.6 feet. In your opinion, if all the human beings currently living on Earth were to stretch out one after the other, how long could they grow? Would this human chain be big enough to go from one end of our planet to the other, passing through its center? Or even to equal the Earth-to-Moon distance? Well, if we estimate that there are currently 7.9 billion human beings on Earth, we get a length of around 13.4 million kilometers, or 8.3 million feet. That's well over the Earth's diameter, which is around 12,700 kilometers, or 7,900 miles. It's also far more than the Earth's circumference, around 40,000 kilometers, or 24,900 miles. But is it enough to cover the Earth-to-Moon distance? Well, yes. In fact, our natural satellite is not as far away as you might think. But we still have to travel some 400,000 kilometers, or 248,000 miles to reach it. However, our human chain would be far too short to reach the various planets in our solar system, starting with our nearest neighbor, Venus. Depending on the era, the distance between the Earth and its sister planet varies between 43 million kilometers, or 26 million miles, and 256 million kilometers, or 159 million miles. This is because the two planets have different periods of revolution around the Sun. Over the decades, they move towards and away from each other in a never-ending cycle. We've now entered the cosmos. Even if we stay within the solar system, which is only a tiny fraction of our galaxy, which itself is dust in the universe, the orders of magnitude are already beyond our comprehension. But that doesn't stop us from marveling at the most immense objects dotting the sidereal void. Let's start by looking around us to see which is the largest telluric planet. If the term doesn't ring a bell, we're talking about rocky planets composed essentially of rock and metal. Compared with gas giants, they are tiny, but their density is high. They are also characterized by the presence of water, in solid or liquid form, an element essential to the formation of life as we know it. In our solar system, there are 4 telluric planets. Classified according to their increasing distance from the Sun, they are Mercury, Venus, Earth, and Mars. Some may notice that Pluto is missing from the list, but this is no oversight. Indeed, due to its small size and haphazard orbit, Pluto, once considered the 9th planet in the solar system, was downgraded to dwarf planet status in August 2006, following a vote by the International Astronomical Union. That said, it remains one of the largest dwarf planets in the solar system, along with Eris, Ceres, Makemake, and Haumea, with a diameter of nearly 2,400 kilometers, or 1,490 miles. It is therefore 6 times smaller than the Earth, but that doesn't stop it from having its own satellites. The largest of these, Charon, is more than half the size of Pluto. It's as if our moon were the size of Mars. But back to our telluric planets. Which is the biggest? Is it Venus? Well, no. It's the Earth at the top of the podium. At the bottom is Mercury. Almost 3 times smaller and 20 times less massive than Earth, it's literally no match. Next comes Mars, which is almost 2 times smaller than our planet. In second place is Venus, with its rather inhospitable conditions. With atmospheric pressure 92 times higher than on Earth, heat of 462 degrees Celsius, or 863 degrees Fahrenheit, sulfuric acid rain, and winds of 400 kilometers per hour, or 250 miles per hour, the Shepherd's star is not a good place to live. And yet, if its atmospheric composition had been different, Venus could have been an excellent candidate for a space colonization project. 1.16 times smaller than Earth, it also has a gravity very close to our own. We also know that water is present on Venus, but mainly in the form of vapor in its atmosphere. However, the presence of frozen water at depth cannot be ruled out. Unfortunately, given the distance separating us from Venus and the technical challenges posed by its atmosphere, colonizing Venus will probably remain a utopian dream forever. We now know that the Earth is the largest telluric planet in the solar system. But what's the biggest moon in it? To find out, we need to turn to the gas giants. Perhaps you're thinking of Titan? A colossal satellite almost as big as Mars orbiting Saturn. But Jupiter is home to the largest moon ever discovered. Its name, Ganymede. It crushes the 91 or so other moons of the gas giant. With a diameter of 5,268 kilometers, or 3,270 miles, 8% larger than the planet Mercury and 2% larger than Titan, it is the largest moon in the entire solar system. However, its strange composition makes it rather less massive than the telluric planets. Ganymede is indeed the heaviest planetary satellite we know of, but its mass is equivalent to 45% of Mercury's, despite its larger dimensions. This is partly explained by the presence of an immense ocean beneath its frozen surface, which could contain more water than there is on Earth. Logically enough, if Ganymede is the king of the solar system's satellites, Jupiter, its home planet, is the queen. 11 times bigger than our blue planet and 318 times more massive, it's a veritable cosmic monster. In terms of volume, it could easily contain all the rocky planets and moons in the solar system. In fact, it would happily swallow up no less than 1,300 Earths. And with a diameter of over 140,000 kilometers, or 87,000 miles, it easily dwarfs all the other planets around it, including Saturn if we ignore its rings. Its atmosphere, churned up by gust storms and giant hurricanes, is mainly made up of hydrogen and helium, like the stars themselves. But at its heart, the great Jupiter is said to harbor a solid core. A ball of matter resembling the Earth, but 14 to 18 times more massive. This stony core would also be covered in ice and contain a metallic core, made of an alloy of iron and nickel. Jupiter is also home to the Great Red Spot, a vast oval-shaped storm of colossal size, enough to swallow the Earth 3 times over. Not to mention the violent winds that swirl around its surface, sometimes exceeding 1,400 kilometers per hour, or 870 miles per hour. By comparison, the strongest winds ever recorded on Earth were just over 400 kilometers per hour, or 250 miles per hour. Despite this blood-curdling description, Jupiter is far from being a threat to us. On the contrary, it plays a protective role, deflecting asteroids and comets that are on a potentially dangerous trajectory for the Earth. Some scientists even believe that the gas giant is one of the reasons why life was able to develop on Earth without being totally wiped out by a series of cosmic collisions. There are many objects in the solar system that threaten us. Masses of rock and ice, drifting at breakneck speeds, waiting for the right opportunity to collide with us. Most of the asteroids we know are located either in the asteroid belt, behind the orbit of Mars, or in the Kuiper belt behind Neptune. But others are more devious, waiting in the shadows to cross our path one day. However, even if the Earth escapes the various threats of the cosmos, there is one that it will never be able to avoid. And paradoxically enough, it's this very threat that is the origin of life: the Sun. Both creator and destroyer, the Sun has been at the heart of many beliefs throughout human history. Its rays provide the energy needed to warm our atmosphere and enable photosynthesis in plants. Without it, we would never have seen the light of day, literally or figuratively. However, assuming we live another 5 billion years, we cannot escape the tragic end in store for our star. Today, what's known as a yellow dwarf, although ironically its volume is large enough to hold 1.3 million Earths. If our planet were 1.2 centimeters or 0.5 inches in diameter, the Sun would be 1.4 meters or over 13 feet in diameter. Even Jupiter, the largest planet in the solar system, is 10 times smaller by comparison. The Sun alone accounts for 99.86% of the solar system's total mass. And yet, our star is far from having reached its final size. At around 4.6 billion years old, it's estimated to be about halfway through its life. In its interior, nuclear fusion is taking place, resulting in a core temperature of around 15 million degrees Celsius, or 27 million degrees Fahrenheit. This fusion is the source of the Sun's heat and radiation. But like everything else in this world, our Sun is not eternal. The day will come when the Sun will have exhausted all its fuel reserves. It will then begin a slow descent into hell, starting with its expansion into a red giant. At the heart of our star, hydrogen atoms fuse to form helium atoms. This high-energy reaction generates incredible pressure, which tends to expand the star. At the same time, the force of gravity acts to compress the Sun. This balance guarantees the stability of our star. But little by little, the amount of helium in the core increases as the hydrogen is consumed. Eventually, the pressure exerted by fusion will decrease sufficiently to cause the core to contract. This will increase the temperature and pressure in the outer layers of the core. As a result, the hydrogen fusion zone will begin to extend beyond the core, towards the outer layers of the Sun. Hydrogen outside the core will be hot and dense enough to undergo nuclear fusion. Our star will then begin its transformation into a red giant. As the fusion zone expands, the core will continue to contract, while the outer layers of the Sun will begin to expand. Our star will begin to inflate like a balloon. It will first engulf Mercury, then Venus, but the fate of the Earth is less certain. Our planet lies on the edge of the zone where the Sun is set to expand, becoming a red giant. As the Sun expands, its radiation will increase considerably. Its surface will be hotter than before, resulting in increased luminosity. Eventually, the Sun will shed its outer layers into space, in the form of solar winds and jets of matter. These expelled layers will form an envelope of gas and dust around the core, creating a planetary nebula. This marks the end of the red giant phase. All that will remain is a dense hot core called a white dwarf, the only vestige of a star that was once resplendent. This white dwarf will be composed mainly of helium and carbon. It will no longer burn fuel, but will continue to glow for a while, emitting residual heat. Then it too will gradually cool down. It will cease to glow and become a dark relic in the darkness of space. In a way, this ending is melancholy sweetness. All the more so when you consider the fate of supermassive stars, which die in a tremendous cosmic explosion called a supernova. All stars and celestial bodies, no matter how immense, will one day come to an end. So before they disappear forever into the sidereal void, let's take advantage of the fact that they are still visible to set off on a voyage of discovery. After starting out in the infinitely small and arriving at the limits of our solar system, it's time for us to go further, much further. Get ready, because we're about to continue our journey into the immensity of our entire universe. Together, we're going to discover the most gigantic objects in the cosmos. In our solar system, we know that Jupiter is the largest of all the planets. Yet across the vastness of our universe and the trillions of billions of galaxies it harbors, there are bound to be stars orbiting a star whose size would make our local giant look like a dwarf planet. Exoplanets so massive, they could be compared to small stars. Well, at the risk of disappointing you, it's unlikely that such planets exist, for the simple reason that too much matter collapses gravitationally, generating sufficient temperature and pressure to trigger nuclear fusion. As a result, what could have become a giant planet often becomes a star. As a result, the largest exoplanets ever discovered are similar in size to Jupiter, although they may be more massive. Such is the case of Kepler 1647b, an exoplanet detected by NASA's Kepler Space Telescope and located nearly 3,700 light-years from us. Its discovery was announced in June 2016, and since then, it has been heralded as the largest exoplanet ever discovered. Its mass and diameter are said to be similar to those of Jupiter. However, Kepler 1647b has an interesting feature. It is a circumbinary exoplanet. This means it orbits two stars comparable to our own Sun. This particular arrangement of stars is reminiscent of the famous sand planet Tatooine from the Star Wars saga. According to the astronomers' observations, Kepler 1647b takes around 3 years to orbit this binary system. This is an interesting discovery, as it places the giant in the system's habitable zone. In other words, it orbits at a distance where the appearance of liquid water is likely. However, Kepler 1647b is a gas planet. It is therefore unlikely to harbor life as we know it. On the other hand, like Jupiter or Saturn, it could have rocky moons, which could then offer much more favorable conditions. Now, if you point a pair of binoculars at the constellation Centauri, you'll be able to spot a young star comparable to the Sun. Located just 310 light-years from Earth, it's called HD 114082. We're not interested in this star, however, but in the exoplanet orbiting it. Named HD 114082b after its star, it is another gas giant. The surprising thing about this star is that its radius is similar to that of our beloved Jupiter. Yet its mass is 8 times greater, some 2,500 times the mass of the Earth. Simply gigantic. Another surprising fact about this super Jupiter, as astronomers call it, is that it orbits very close to its star, about half the distance to the Sun. As a result, its period of revolution is just 110 days. By comparison, Jupiter takes 12 years to orbit the Sun, and Neptune, the most distant gas giant in our solar system, takes 165 years to make a complete revolution. HD 114082b is also the youngest known gas giant whose radius and mass have been determined. But something's not quite right. Based on current models that determine the maximum size and mass that planets can have, our super Jupiter is around 2 to 3 times too dense for such a young gas giant. How can this anomaly be explained? There are several hypotheses. First, it could be that an error was made in the measurements. But with this kind of discovery, the data is always checked several times. Another possibility is that the models used by the astronomers are incorrect. Finally, it's possible that HD 114082b is an anomaly, a kind of cosmic scale error of nature, with an unusually large solid core, which would explain its incredible density. For the moment, the question remains unanswered, and we'll have to wait for further discoveries before we have a definitive answer to this enigma. Speaking of cosmic anomalies, we can also mention the case of AB Aurigae b, also known as ABRB. This is a gas giant exoplanet with a mass 9 times that of Jupiter. This makes it the most massive exoplanet ever discovered. It lies some 508 light-years from Earth. What makes it so spectacular is not just its extraordinary mass. Rather, it's the fact that it's the first directly observed exoplanet still embedded in the disk of gas and dust from which planets are formed. This is known as the protoplanetary disk. To explain the birth of stars, researchers put forward 2 hypotheses. The first is called core accretion. The material making up the disk condenses by accretion until it forms a solid core, essentially made up of rocky materials and metals. Once this core has reached critical mass, it in turn accretes gases, mainly hydrogen and helium, until it forms a gas giant planet, The second hypothesis is that of disk instability. This involves the collapse of parts of the protoplanetary disk under the effect of gravitation. This collapse condenses the material to form a gas-only planet with no rocky core. Given the vast distance separating AB/B from its star, almost 93 times the distance from the Earth to the Sun, astronomers are leaning towards the disk instability model to explain its formation. The shape of the spiral arms of the protoplanetary disks surrounding the star also supports this hypothesis. Having a direct image of AB/B's formation around its star is therefore proof that gas giants can form through disk instability. At least it's an observation that calls into question standard models of planet formation. This is because until now, the vast majority of exoplanets observed had orbits around their stars that did not exceed the distance between the Sun and Neptune. However, AB/B orbits 3 times further than Neptune from the Sun. Unfortunately, it's still too early to say anything about this strange giant planet. In fact, it's only at the beginning of its formation process, rather like a fetus in gestation. It is even approaching the maximum size to be classified as a planet, rather than a brown dwarf. In other words, an aborted star too small to trigger a stable hydrogen fusion process. These stars are halfway between stars and planets, condemned never to shine. Be that as it may, the discovery of AB/B is just further proof of just how complex the mechanisms governing our universe really are. New astronomical observations continually challenge our current theories, improving our understanding of the universe. Planet formation is highly complex and messy, and there are still many surprises in store for us. And we're going to continue our discovery of those surprises. This time, we're going to focus on the telluric planets, i.e. the rocky planets. Just as there are super Jupiters, there are also super Earths, which make our blue planet look like a small moon. One of the most famous of these is HD 219134b. When its discovery was announced on July 30th, 2015, it was the closest telluric exoplanet to Earth ever discovered, just 21 light-years away. But today, that title goes to Proxima Centauri b, which is 4.2 light-years away. That said, HD 219134b is still quite close, and assuming we could ever travel at the speed of light, getting there would not be impossible. However, it's not in its star's habitable zone, so an expedition there seems a bit pointless. All the more so as its surface temperature exceeds 400 degrees Celsius, a veritable furnace. But the reason why HD 219134b is of such interest to scientists is that its proximity allows for a more in-depth study of neighboring telluric planets outside our solar system. Similar to our own planet, in terms of composition and density, Super-Earth HD 219134b differs above all in its radius and mass. These two parameters are respectively 1.6 and 4.5 times greater than those of the Earth. This may sound huge, but it's nothing compared to the planet that is still considered the most enormous of all rocky planets ever discovered. Its name? Kepler 10c. This exoplanet was detected by NASA's Kepler Space Telescope in 2011. It lies around 560 light-years from Earth in the constellation Dragon. Until then, the telluric planets discovered had masses equivalent to 10 times that of Earth for the largest, but the discovery of Kepler-10c has put things into perspective. This mega-Earth is 17 times more massive than our planet, with a radius 2 times greater. Yet it has the same density. Before its discovery, theorists believed that such planets could not exist. Their argument was that beyond a certain mass, the solid body must capture the surrounding gases, as well as those it produces, to gradually metamorphose into a gas giant. However, this is not the case with Kepler-10c, which remains an enigma for science. In fact, early observations of this star only hinted at its size, so astronomers thought it must be a Neptune-like planet. The surprise came when Kepler-10c's mass was finally measured. Another troubling fact about this star concerns its age. The giant planet is thought to be around 10 billion years old. At that time, the first generation of stars had only just completed their life cycle, and the heavy elements needed to form rocky planets were not very abundant in the universe. Proof that there are certainly worlds similar to our own, but much older in the cosmos. Worlds that could potentially have been home to life for billions of years, giving organisms time to evolve and perhaps even travel to other planets. Although this is purely speculative, it does give us confidence that we may one day encounter other intelligent life forms. Among the bestiary of ultramassive telluric planets, TOI 849b by its scientific name. On NASA's official website, it's presented as a gas giant, yet there's hardly a gaseous envelope to be found on this planet. Only a solid body 3.5 times larger than the Earth, and 40 times more massive. TOI 849b is about the same size as Neptune, but outweighs it by 2.3 times in terms of mass. It is one of the densest planets of its size ever observed. But in reality, TOI 849b doesn't deserve the title of super-Earth, since it is in fact the residual core of a gas giant. TOI 849b could be a reflection of Saturn or Jupiter, should they lose their gas envelope. This hypothesis seems highly likely, given that TOI 849b orbits so close to its star that it circles it in less than a day. It therefore receives 2,000 times more radiation than we do from the Sun. Its gaseous layers may well have been swept away by its star. If this scenario is correct, TOI 849b would be the largest known gas giant core. However, one question remains. If TOI 849b's gas envelope was indeed blown away by its star, how come there's still a residual part of it? Only more detailed observations will one day be able to solve this planetary mystery. Perhaps even telescopes will one day point their sensors at even more monstrous planets, putting astrophysicist models to an even greater test. In any case, if we want to see in detail what the largest objects in the universe are, we can't limit ourselves to planets. We need to go one step further, one step higher, to the stars. Earlier, we saw that within the solar system, nothing compares to the Sun's 1.4 million kilometer diameter. And yet, as imposing as it is in comparison to us, it's just a speck of dust compared to the biggest star we know. Until recently, this record was held by VY Canis Majoris, a red supergiant star in our galaxy 5,000 light-years away, To our eyes, its size seems infinite. 2 billion kilometers in diameter, or around 13 times the distance from the Earth to the Sun. If Vy Canis Majoris stood in the place of our Sun, it would be large enough to engulf our solar system all the way to Jupiter. Its size is therefore around 1,500 times that of our star, which in comparison would be no bigger than a football against the Eiffel Tower. But the biggest star we know today is not Vy Canis Majoris, but Uy Scuti, another red supergiant located in the Sobieski Shield constellation, 9,500 light-years away. 1,700 times larger than the Sun, it could extend as far as Saturn if placed at the center of the solar system. However, when we talk about giant stars, we also need to consider their mass. Indeed, while Uy Scuti is the largest of them all, the title of the most massive known star goes to R136A1. It weighs around 250 solar masses, whereas astrophysicist limits for stars are more like 150 solar masses. What's more, R136A1 is also one of the brightest stars in the cosmos, shining as brightly as 10 million suns combined. Located within the Tarantula Nebula in the Large Magellanic Cloud, a dwarf galaxy close to the Milky Way, its position makes it difficult to observe. In fact, the star is part of the R136 supercluster of stars, 9 of which have a mass more than 100 times that of the Sun. Researchers had to make several measurements and observations to correctly identify all the stars in the R136A group, itself part of the R136 star cluster. Interestingly, R136A1 is located in the Tarantula Nebula, which, as well as being spectacular, is also the largest we know of. It extends over a vast region of space covering some 1,000 light-years. That's around 9.5 million billion kilometers. It's so large that it's even visible to the naked eye from the southern hemisphere. It's even a popular target for amateur astronomers. The Tarantula Nebula is also a cosmic wonder, offering fertile ground for astronomers studying star formation and death. In 1987, a brilliant supernova occurred within the nebula, enabling astronomers to study this prodigious cosmic phenomenon at close quarters. Also in the nebula family is the Orion Nebula. Visible to the naked eye as a blur in the sky near Orion's belt, it is one of the brightest and most accessible nebulae for observers of the cosmos. It occupies an area of sky 4 times larger than that covered by the full moon. Its size is around 24 light-years, but it's its proximity to Earth that makes it so visible. The Orion Nebula also owes its shimmering colors to hot young stars that emit intense ultraviolet light. This light excites the surrounding gas, mainly hydrogen, which then glows in different visible colors, giving the nebula its characteristic brilliance. This is the case for most nebulae, which are ideal zones for the formation of star clusters. Nebulae are nothing more than vast clouds of gas and dust in space. They contain all the elements necessary for star formation. When a nebula collapses under the influence of gravity, it creates regions of concentrated matter, known as protostellar cores. These cores are dense clusters of gas and dust, with high temperatures and pressures. Under these conditions, matter continues to accumulate and collapse, until nuclear reactions are triggered in the core. This event marks the birth of a new star. When a large number of protostellar cores form within a nebula, they can eventually give rise to star clusters. The stars in the cluster thus share a common origin and are often gravitationally linked to one another. There are two types of cluster. Firstly, there are open clusters. These are clusters of young bright stars that are also massive and hot. Open clusters generally contain a few dozen to a few thousand stars and are scattered over a relatively vast area. Then there are globular clusters. These are clusters composed mainly of stars that are older and less massive than those in open clusters. Globular clusters typically contain hundreds of thousands to millions of stars and are also very dense. They owe their name to their spherical structure, which gives them a globular appearance. In the Milky Way alone, researchers have identified over 150 such clusters. One of the best known is undoubtedly M13, the large cluster in the constellation of Hercules. Located some 22,000 light-years from Earth, M13 has fascinated astronomers for centuries. Both massive and very compact, it's difficult to say exactly how many stars it contains. Estimates range from a few 100,000 to several million stars, tightly packed into a sphere, around 145 light-years in diameter. In the night sky, its apparent diameter is about half that of the full moon. The M13 cluster is also one of the oldest objects in our Milky Way. It is around 12 to 13 billion years old. It was therefore formed very early in the history of the universe, which was born around 14 billion years ago. The stars making up the Hercules cluster are predominantly low-mass, low-metallicity stars. In other words, they contain relatively small quantities of elements heavier than helium. There's also an interesting anecdote about this globular cluster. In 1974, M13 was chosen to send an interstellar message in the hope that one day an extraterrestrial civilization might receive it. Unfortunately, the chances of ever receiving a reply to this message are slim. So if there are no little green men in the Milky Way, we may have to look elsewhere. And why not in Andromeda? After all, it's the closest galaxy to us if we exclude dwarf galaxies. Located around 2.5 million light-years from Earth, Andromeda and the Milky Way appear to be closing in on each other at high speed. So much so that one day the two will collide to form a huge elliptical galaxy called Milkomeda. But rest assured, this won't happen for another 4 billion years. The Milky Way has a radius of around 52,850 light-years. Andromeda, on the other hand, has a radius of almost 110,000 light-years. It would contain around 1,000 billion stars. That's 2 to 5 times more than our own galaxy, which makes it 25% brighter than our beloved Milky Way. And yet, despite its impressive dimensions, Andromeda pales in comparison to the largest galaxy known to date, IC 1101. IC 1101 is a monstrous elliptical galaxy in the farthest reaches of the cosmos, 1 billion light-years away. Its diameter, mind you, is 6 million light-years. It's also home to over 100,000 billion stars, giving it a mass 2,000 times greater than that of the Milky Way. It's simply unimaginable. But in February 2022, another contender emerged to challenge for the crown. This galaxy is Alcyone, a cosmic monster 16.3 million light-years long. In reality, Alcyonia is not quite a galaxy, but rather a radio galaxy. This means that it emits radiation at very specific wavelengths. Radio galaxies are characterized by their intense emission of radio radiation, which comes from their active, supermassive nuclei. They are generally divided into two main categories: double-lobe radio galaxies and double-jet radio galaxies. The former have a Y or X-shaped structure, with two symmetrical lobes on either side of the central nucleus. Each lobe is made up of matter ejected at speeds close to the speed of light. They are the result of the presence of an active supermassive black hole in the middle of the galaxy. Double-jet radio galaxies feature narrow jets of matter ejected from the central nucleus at near light speeds. But unlike double-jet radio galaxies, they have no extended lobes. In any case, the behavior of radio galaxies is thought to be due to the presence of supermassive black holes at their centers. The latter actively absorb the surrounding matter, releasing an enormous amount of energy. This then manifests itself in the form of radiation of various wavelengths, including radio waves. These radio emissions come mainly from matter heated and accelerated by relativistic particle jets in the vicinity of the central black hole. This is why radio galaxies are an important object of study in astrophysics. They provide essential information on the processes of matter accretion around supermassive black holes. They also enable us to better understand the impact of these cosmic chasms on the evolution of galaxies and the universe on a large scale. Speaking of black holes, the one at the center of Alcyonia is not as gigantic as you might think. In fact, both Alcyone's stellar mass and the mass of its supermassive black hole are lower than those of other giant radio galaxies discovered previously. That said, it is still 100 times more massive than the black hole at the center of the Milky Way. So the largest known galaxy doesn't have the biggest black hole we've ever seen. But where is it hiding? The answer lies 700 million light-years away in a supergiant elliptical galaxy, the brightest in the Abell 85 cluster. This is Holmberg 15a, also known as Holm 15a. Around 3 times larger than the Milky Way, this distant cousin harbors at its center the largest world devourer ever discovered. Not a supermassive black hole, but an ultramassive one. 40 billion solar masses. The size of the associated event horizon, the limit beyond which nothing, not even light, can escape its pull, is simply unimaginable. Nearly 800 times the distance between the Earth and the Sun. That's 10,000 times the distance to the supermassive black hole at the center of our Milky Way. So far, we've seen that there are planets, stars, galaxies, and even giant black holes. We've also seen that stars can group together to form clusters. But what you may not know is that galaxies also form clusters. They entwine along a cosmic web to form complex structures of staggering size. These are known as supergalaxy clusters. Imagine a multitude of cosmic islands made up of billions of stars, grouped together in a colossal assemblage, like pieces of an immense cosmic puzzle. That's exactly what a supercluster is. To put it more simply, it's a large-scale cosmic structure made up of multiple galaxy clusters. And the clusters themselves are groups, sometimes containing up to several thousand galaxies. Superclusters can therefore group together dozens or even hundreds of clusters, creating a structure of colossal size. These cosmic giants extend over megaparsecs, an astronomical unit of measurement equivalent to more than 3 million light-years. Gravitational force is both the driving force and the cement of these astronomical constructions. Gravity pulls galaxy clusters together, forming a compact, massive whole that spreads across the fabric of space-time. This creates an environment where galaxies of all shapes and sizes cohabit, exchanging gas and stars and interacting gravitationally. Over time, superclusters continue to assemble, constantly drawing new galaxy clusters into their orbit. They also evolve through collisions with other superclusters, creating cosmic interactions of extraordinary complexity. Their discovery and study are of crucial importance to cosmology. They help us to understand the distribution of matter in the universe, as well as the dynamic forces that shape the evolution of galaxies over time. Now let's delve into the heart of these immense structures. Let's take a closer look at one of these superclusters that particularly arouses our curiosity and admiration, Laniakea. The name Laniakea comes from the Hawaiian word for celestial immensity. It's a fitting name given the sheer size of the structure. Laniakea extends over an area around 500 million light-years in diameter. That's almost 5,000 times the size of our own Milky Way galaxy. When we speak of Laniakea, we're talking about a supercluster of galaxies, a gargantuan collection of individual groups of galaxy clusters that span vast regions of space. And at the heart of this vastness lies our own galaxy, the Milky Way. Floating like a grain of sand on the edge of an infinite beach. Every point of light you see represents billions of stars, planets, gas, and dust. From up here, Laniakea looks like a brilliant constellation, its contours defined by the movements and attractions of the galaxies that make it up. Laniakea's interior is a complex collection of galactic filaments, dense clusters, and vast voids. These filaments are in fact cosmic highways, where galaxies migrate and interact under the influence of gravitational forces. It's a complex cosmic dance, in which each participant is linked by the invisible chains of gravity. The Milky Way, with its distinctive spiral, and our neighbor, the Andromeda Galaxy, are part of the Local Group, a cluster of galaxies belonging to the Virgo supercluster, itself part of Laniakea. Laniakea does not stand alone in the vastness of space. It is in constant interaction with other neighboring superclusters, such as the Perseus-Pegasus supercluster. These interactions on a cosmic scale shape the evolutionary landscape of the universe. But why are these structures so important to scientists? By studying superclusters, we can better understand how matter agglomerated after the Big Bang, and how galaxies formed and evolved. Ultimately, Laniakea is not just a supercluster of galaxies. It is a witness to cosmic evolution, a milestone in our understanding of the universe, and perhaps most importantly, our home in the great cosmos. And what's even more fascinating is that Laniakea itself is just one of many superclusters. It accounts for just 4% of the observable universe. Our celestial immensity is actually connected to other superclusters, forming even larger structures, and an eternal celestial dance orchestrated by gravity. It was by conducting these studies on very large scales that astronomers were able to identify what is to date the largest and most massive known structure in the observable universe, the Great Wall of Hercules Boreal Crown, a fitting name for this gigantic galactic filament. Discovered by chance in 2013, following a gamma-ray burst mapping program, the Great Wall of Hercules is, so to speak, a supercluster of superclusters of galaxies. It measures almost 10 billion light-years by 7.2, making it 900 million light-years thick. It contains tens of thousands of galaxies and lies 10 billion light-years from us. By way of comparison, the diameter of the observable universe is 93 billion light-years. The Great Wall of Hercules therefore represents around 10% of the observable universe. Within the wall, galaxy clusters and superclusters are interconnected by filaments of hot gas. Since its discovery, researchers believe that other, potentially even larger, similar structures lurk in the darkness of the sidereal void, waiting to be discovered. Together, they would form the great web of the universe. If, from our perspective, galaxies and matter scattered throughout the cosmos seem to be scattered randomly, in a kind of infinite chaos, galactic filaments put this vision into perspective. In the end, things seem far more orderly than they appear at first glance. A bit like atoms coming together to form molecules on a microscopic scale. Other galactic fabrics have been discovered in recent years. Such is the case of the Great Sloan Wall, which for a decade was considered the largest structure in the universe, before the Great Wall of Hercules Boreal Crown took its title. With a length of 1.3 billion light-years, it was a worthy challenger, no pun intended. It was spotted in 2003, thanks to data from the Sloan Digital Sky Survey, SDSS, spectroscopic survey. Even more recently, Boss's Great Wall came to the fore. More modest than the previous two, it is nonetheless an impressive network, comprising 4 superclusters of galaxies. It is estimated that at least 830 galaxies are trapped in its nets, giving it a mass equivalent to 10,000 times that of our own Milky Way. As discoveries progress, the galactic fabrics or filaments known as the wall lose their anomalous status. On the contrary, these formations are as widespread as stellar or planetary systems within galaxies. In fact, there are even stranger cosmic formations than clusters or walls. They're called superstellar bubbles. These are enormous cavities or spherical structures scattered throughout the interstellar medium. Stellar superbubbles are created by the explosive activity of multiple massive stars, notably supernovae and stellar winds. Supernovae are cataclysmic explosions that occur when a massive star exhausts its nuclear fuel and collapses in on itself, releasing a colossal amount of energy. Stellar winds, on the other hand, are constant ejections of matter from the surface of massive stars during their active life. Massive stars eject large quantities of matter, energy, and particles at high speed during their explosion and aging phases. The formation of superbubbles begins when these giants reach the end of their life cycle. These phenomena expel matter and energy into the surrounding space. If several massive stars form in a given region of a galaxy, their combined explosions and ejections can create a huge cavity in the interstellar medium, forming a stellar superbubble. Inside these superbubbles, the gas expelled by the stars mixes with the surrounding interstellar gas, creating dense hot regions. The shock waves generated by the explosions propagate through the interstellar medium, compressing the surrounding matter and promoting the birth of new stars. Superbubbles can extend over hundreds to thousands of light years. They are therefore just one of the many forms that large-scale cosmic structures can take. Once again, they reflect the diversity of phenomena and creative processes that take place within our universe. Magnificent cataclysms which give rise to the most terrifying explosions, but also to the most beautiful creations that man can observe. Far, far away, lost on our blue planet, we'll continue to scan the skies in search of these events that are beyond our comprehension in an attempt to unravel their secrets. Ridiculous as we are in the face of cosmic immensity, our thirst for discovery, but perhaps also our natural ego, leads us to believe that one day infinity will reveal its secrets to us. Throughout our journey, we've been able to admire many of the cosmic immensities that dot our universe. But however large and imposing these entities may be, they all remain measurable. This raises a crucial question. Does the universe have an end? Is it just a huge bubble filled with galaxies, stars, black holes, and other stellar objects? And if so, what surrounds this bubble? Is it nothingness or something even more vast? As soon as we take the slightest interest in the cosmos, all these dizzying questions inevitably come to mind, to the point of making us feel uneasy, because these questions confront us with the limits of our own understanding. We may understand the principle of infinity, but we can't visualize it clearly in our minds. It's as if we're missing some key to understanding. An emptiness that means we can't put our finger precisely on certain concepts to grasp all their nuances. And then comes the ultimate question. Are the secrets of the universe meant to be understood by man? Or are they, by their very nature, forever inaccessible to us? Taking the thought process a step further, we might even wonder whether understanding all the workings of the world around us would make our existence more meaningful. After all, isn't it this perpetual lack of understanding and the mysteries that lie before us that drive us to live to discover them? It's up to you to find the answer. Perhaps it will lead you to other questions, which will continue to fuel the flame of your curiosity. That burning desire to seek the truth, to understand how things work. In the end, perhaps that's the greatest strength of the human race.